Scientists just measured gravity at the quantum scale for the first time in 2024, and it's behaving completely wrong. The gravitational constant, the number that's supposed to be the same everywhere in the universe, changes by 0.15% depending on how you measure it. That's impossible. And it gets worse. Every physics equation you've ever learned, every GPS satellite orbiting Earth, every rocket trajectory NASA calculates, all of them use a version of gravity that might be fundamentally broken. The force holding you to the ground right now, we don't actually know what it is. According to Newton and Einstein, gravity is a constant force determined by mass and distance. Here's the problem. When quantum physicists try to measure it at the smallest scales, it doesn't work that way at all. Think of it like this. You've been told your whole life that water is wet. Then someone zooms in with an electron microscope and discovers water molecules are actually dry. That's what's happening with gravity right now. For 6 months in 2023, a team at the University of Southampton tried to reconcile two measurements of gravity that differed by more than experimental error should allow. First theory, equipment calibration error. They recalibrated everything. The discrepancy remained. Second theory, environmental interference. Maybe Earth's magnetic field or seismic vibrations were throwing off readings. They isolated the experiment in a bunker 100 meters underground. The discrepancy got worse. Then lead physicist Tim Fuchs looked at the data one last time and noticed something that made his hands shake. The measurements weren't wrong. Gravity itself was fluctuating. At distances smaller than 100 micrometers, about the width of a human hair, gravity becomes 0.15% weaker than Newton's law predicts. That's a tiny difference. But here's what breaks your mind. 0.15% is enormous in physics. The entire GPS system would fail if we were off by even 0.01%. 3 separate labs confirmed it. Harvard, Austria, Japan. All found the same anomaly. Gravity at the quantum scale doesn't follow the rules. The force that holds galaxies together, that keeps you from floating into space, that makes apples fall from trees, we've been measuring it wrong for 337 years. But here's what broke them. When they calculated what this means for Einstein's general relativity, the most successful theory in physics history, they discovered something terrifying. If gravity is weaker at small scales, then the universe's expansion rate should be different than what we observe. But it's not. This means either our measurements are still somehow wrong despite triple checking, or there's a fifth fundamental force of nature that we've never detected. Something that compensates for gravity's weakness at quantum scales. Something that's been hiding in plain sight for the entire history of science. Dr. Claudia Durham at Imperial College London said this. We're not tweaking a theory. We're staring into an abyss. Either gravity is wrong or everything else is. This discovery rewrites 3 fundamental things. First, future space missions will need to recalculate every trajectory. The Artemis program taking humans back to the moon? Those calculations assume gravity works the way Newton said. If we're wrong by even 0.1%, astronauts could miss lunar orbit entirely. Second, physics textbooks are being emergency revised right now. The chapter on gravity in your high school physics book, it'll have a warning label by 2026. This is an approximation only. Third, dark matter might not exist. We invented dark matter to explain why galaxies rotate faster than gravity should allow. But if gravity is weaker at small scales and stronger at galactic scales, we might have been chasing a phantom for 90 years. But to understand how we got gravity this catastrophically wrong, we need to go back to 1687, the year Isaac Newton watched an apple fall and thought he understood everything. Newton's law of universal gravitation is beautifully simple. F, G, M1, M2, R2. Force equals the gravitational constant times the masses divided by distance squared. For 228 years, this equation worked perfectly. It predicted planetary orbits. It let us discover Neptune by calculating where an unseen planet must be based on Uranus's wobble. It was so accurate that scientists called it a law of nature. However, in 1915, Einstein revealed a problem. Newton thought gravity was a force, one object pulling another through empty space. Einstein showed that's impossible. Nothing can pull through empty space instantly. Information can't travel faster than light. Instead, Einstein proposed that mass bends space-time itself. Gravity isn't a force. It's geometry. You're not being pulled down to Earth. You're following the straightest possible path through curved space-time. The ground is accelerating up to meet you. This blew everyone's mind. But it worked. Einstein's equations predicted Mercury's orbit perfectly where Newton's failed. They predicted black holes before we ever saw one. They predicted gravitational waves detected in 2015, a century after Einstein wrote them down. But here's where things fall apart. Einstein's general relativity works perfectly at large scales. Planets, stars, galaxies. Quantum mechanics works perfectly at small scales. Atoms, electrons, photons. These are the two most successful theories in science history. The problem? They're completely incompatible. General relativity says space-time is smooth and continuous. Quantum mechanics says everything is choppy and probabilistic. General relativity is deterministic. If you know initial conditions, you can predict the future exactly. Quantum mechanics is fundamentally random. You can only calculate probabilities. For 100 years, physicists have tried to merge them into a theory of everything. String theory, loop quantum gravity, supergravity. Every attempt fails. Because gravity refuses to play by quantum rules. In quantum field theory, every force is carried by a particle. Electromagnetism has photons. The strong nuclear force has gluons. The weak nuclear force has W and Z bosons. Gravity should have gravitons. But we've never detected one. And when physicists try to calculate what gravitons should do, the math breaks. The equations spit out infinities, nonsense answers. It's like asking, what's 1 divided by 0? The universe just shrugs. This brings us back to that impossible measurement in 2024. If you want to test whether gravity follows quantum mechanics, you need to measure it at quantum scales. That means measuring the gravitational attraction between objects smaller than a millimeter. Here's the problem. Gravity is absurdly weak. The electromagnetic force between two electrons is 1042 times stronger than their gravitational attraction. That's 1 followed by 42 zeros. To put that in perspective, the difference between a single atom and the entire observable universe is only about 1090. Gravity is so weak that measuring it at small scales is like trying to detect a whisper during a rocket launch. But in 2023, scientists at Southampton built an experiment clever enough to do it. They suspended a tiny gold sphere, 2 millimeters across, and measured how it attracted an even tinier probe. They isolated it from vibrations, electromagnetic interference, temperature fluctuations, air currents, even cosmic rays, and they found something impossible. The gravitational constant G, which should be 6.6674 x 1011 men 3 kgs2, was actually 6.664 x 1011, a difference of 0.15%. That's like measuring the speed of light and finding it's 299,000 km/s instead of 299,092 km/s. It would break everything. When Tim Fuchs published this result, the physics community went into crisis mode. Extraordinary claims require extraordinary evidence. If gravity really changes at small scales, it would be the biggest physics discovery since quantum mechanics itself. Or it could be a mistake that destroys a career. 3 independent teams rushed to replicate the experiment. Harvard built their own apparatus using a different design. Instead of gold spheres, they used ultra-cold atoms suspended in laser beams. They measured gravity between atoms separated by 50 micrometers. Result? Gravity was 0.14% weaker than expected, nearly identical to Southampton. A team in Vienna used optically levitated nanoparticles, tiny diamonds suspended in laser traps. They measured gravitational attraction between particles only 300 nanometers across. Result: gravity was 0.116% weaker. In Japan, researchers at the University of Tokyo used an entirely different approach. They measured how gravity affects quantum interference patterns. If gravity couples to quantum states, it should change how matter waves interfere. Result: the interference pattern showed gravity behaving 0.15% weaker than general relativity predicts. 4 independent experiments, 4 different methods, all finding the same impossible answer. In October 2024, the International Committee for Weights and Measures held an emergency session. This is the organization that defines fundamental constants: the speed of light, Planck's constant, the gravitational constant, g. For the first time in 50 years, they considered changing the accepted value of a fundamental constant based on new measurements. But here's the crazy part. They couldn't decide what value to change it to, because the discrepancy only appears at small scales. At large scales, say measuring the Earth-Moon gravitational system, g is exactly what Newton predicted. This means g isn't actually constant, it's scale-dependent, and that breaks the entire framework of physics. Dr. Sean Carroll, a physicist at Johns Hopkins, said, "This is worse than finding a new particle or a new force. This is finding out that the playing field itself is wrong. It's like discovering that math doesn't work the same way on Tuesdays." The committee adjourned without a decision. The value of g remains officially unchanged, even though everyone knows it's wrong. However, behind closed doors, something stranger was happening. If gravity is weaker at small scales but correct at large scales, something must be compensating. Some force we've never detected must be filling the gap. Physicists call it the fifth force. We know 4 fundamental forces: gravity, electromagnetism, strong nuclear force, weak nuclear force. Every phenomenon in the universe, from supernovae to your heartbeat, is caused by combinations of these 4. But if a 5th force exists, it would need bizarre properties. First, it would need to be repulsive at quantum scales to counteract gravity's weakness, but attractive at large scales to make galaxies work correctly. Second, it would need to be incredibly weak, strong enough to matter at micrometer scales, but too weak to detect in any previous experiment. Third, it would need to interact with mass, but not electromagnetic charge. Otherwise, we'd have seen it in particle accelerators. Some theoretical physicists think they've found a candidate: moduli fields from string theory. These are hypothetical fields that could vary in strength depending on scale. They're called chameleon fields because they change behavior based on environment. If chameleon fields exist, they could create a repulsive force at small scales that weakens as you zoom out. At galactic scales, the chameleon field would be negligible, and normal gravity dominates. This would explain the discrepancy perfectly, but it would also mean string theory, controversial for decades because it makes no testable predictions, might actually be real. But here's where things get really wild. In the 1970s, astronomer Vera Rubin discovered that galaxies rotate way too fast. The outer edges should fly apart based on the visible matter we can see, but they don't. So, physicists invented dark matter, invisible mass that provides extra gravity to hold galaxies together. For 50 years, we've been searching for dark matter particles. We've built detectors kilometers underground. We've sent satellites to space. We've smashed particles together at near light speed. We've found nothing. What if dark matter doesn't exist? What if galaxies rotate faster than expected because gravity is stronger at galactic scales than we thought? If the gravitational constant changes with scale, then our equations for galactic rotation are wrong. The missing mass we call dark matter might just be incorrect gravity. Several teams are now recalculating galactic rotation curves using scale-dependent gravity. Preliminary results are shocking. Some galaxies don't need any dark matter at all. The rotation curves fit perfectly if you just adjust g by 0.2–0.3% at those distances. However, this creates a new problem. Dark matter also explains galaxy cluster dynamics, gravitational lensing, and the cosmic microwave background. If dark matter doesn't exist, we need to explain all those phenomena differently. Some researchers are trying, but it's like pulling one thread and watching the entire sweater unravel. Not everyone agrees this is a crisis. Dr. Sabine Hossenfelder, a physicist at the Frankfurt Institute for Advanced Studies, argues the discrepancy might be experimental error we haven't identified yet. Every decade, someone claims they've broken general relativity, she wrote. Every decade, they're wrong. Extraordinary claims require extraordinary skepticism. Others point out that scale-dependent gravity creates as many problems as it solves. If g changes with distance, then the orbits of GPS satellites should show detectable errors. They don't. If g changes with mass density, then dense objects like neutron stars should behave differently than observations show. They don't. Critics argue that 4 experiments isn't enough. Physics history is full of experimental anomalies that disappeared with better equipment. The faster-than-light neutrinos detected in 2011 turned out to be a loose cable. But defenders of the new measurements point out something crucial. This time, 4 independent teams using completely different methods all found the same anomaly. That's never happened before with a false positive. Dr. Tim Fuchs, who led the Southampton experiment, responded directly, "We've checked everything 100 times. We've hunted for every possible source of error. Either we're making a mistake that 3 other brilliant teams also made in completely different ways, or gravity really is broken. I know which one I'm betting on." But one result remains unexplained. In March 2024, the Vienna team reported something that shouldn't be possible. During one run of their experiment, the gravitational discrepancy spiked to 0.47%, 3 times larger than normal, for exactly 23 seconds. Then it returned to the expected 0.15%. The spike happened at 3:17 a.m. local time. During those 23 seconds, the nanoparticles in their experiment behaved as if gravity had suddenly become 3 times weaker. They thought it was a glitch, but when they checked their logs, everything was normal. No power surges, no seismic activity, no electromagnetic interference, no equipment failures. Then they checked the timestamps. At exactly the same moment their anomaly spiked, the Harvard team's experiment, running simultaneously 6,000 kilometers away, detected a 0.44% spike lasting 22 seconds. 2 independent experiments, separated by an ocean, detecting the same impossible fluctuation at the same moment. The teams cross-referenced with astronomical data. No solar flares, no gravitational wave events detected by LIGO, no gamma-ray bursts. Nothing in the observable universe that could explain synchronized quantum gravity fluctuations on 2 continents. They haven't published this data yet. It's too strange. But it's been confirmed in private communications between labs. Something made gravity fluctuate for 23 seconds. And we have no idea what. The Quantum Gravity Explorer satellite launches in 2027. It's specifically designed to measure gravity at quantum scales in space. On Earth, every gravity experiment fights against seismic noise, thermal vibrations, and electromagnetic interference. In orbit, those problems disappear. The QGE will measure gravitational interactions between test masses in pure vacuum, isolated from Earth's influence. If the 0.15% discrepancy persists in space, it confirms the anomaly is real. If it disappears, it means something about Earth's environment is affecting measurements in ways we don't understand. But here's the crazy part. If gravity really is scale-dependent, then QGE might detect something even stranger. In orbit, test masses will experience microgravity, almost perfect freefall. That's a completely different gravitational environment than any Earth-based experiment. Some theorists predict that in microgravity, the quantum anomaly could be 10 times larger. Instead of 0.15%, we might see deviations of 1 to 2%. That would be unmistakable, undeniable, physics-breaking. Or QGE might find nothing. The anomaly might disappear in space, proving it was an experimental artifact all along. Every lab that claimed to detect it would have to retract their papers. The crisis would end. But privately, physicists are preparing for the opposite, because if 4 independent teams found the same anomaly using different methods, and if 2 of them detected synchronized fluctuations across continents, then something very strange is happening to gravity, and we're about to find out what. So here's my question. What do you think is causing the gravitational discrepancy? Option A, experimental error that will be debunked. Option B, a 5th fundamental force we've never detected. Option C, scale-dependent gravity that rewrites general relativity. Option D, something even stranger. Drop your answer in the comments. I'll pin the most creative explanation. And here's a harder question. If dark matter doesn't exist and it's actually modified gravity, how do we explain galaxy clusters and gravitational lensing? Seriously, physicists are struggling with this. If you have an idea, comment it. Also, poll time. Do you think Einstein's general relativity will still be taught as correct in 50 years? Or will we look back on it like we look back on Newton, brilliant but incomplete? The Quantum Gravity Explorer launches in 2027. By 2028, we'll know if this is the biggest physics discovery in 100 years or the most embarrassing false alarm. Subscribe now so you don't miss it. Turn on notifications. This story is just beginning. I'll be covering every milestone, the launch, the first results, and what happens when physicists either confirm or disprove scale-dependent gravity. The next video in this series drops when QGE releases preliminary data. You'll want to be here for that. Next week, the parallel universe hypothesis just got evidence. Quantum computers detected particles that shouldn't exist in our reality. They're calling it shadow matter, and it might prove the multiverse is real.